At 5:45 on the morning of the 16th of May, 1968, a woman named Ivy Hodge walked into her kitchen on the 18th floor of a brand new London tower block, filled a kettle, and struck a match to light the stove for a cup of tea. The building was 2 months old. It was meant to stand for 60 years. What happened in the next few seconds instead was that a small explosion, not even a large one, knocked out a single wall panel, and the entire southeast corner of that 22-story tower peeled away and fell to the ground, floor after floor, all the way down, like one side of a house of cards. 4 people died. And here's the part that changed engineering forever. Ivy Hodge survived. The explosion that started it was small enough to walk away from. The building was the thing that killed. We'll get to exactly why. To understand Ronan Point, you have to understand the Britain that built it. After the Second World War, London had a housing crisis of staggering scale. Bomb damage, slums, and hundreds of thousands of families on waiting lists for a decent home. The answer, embraced across the country in the 1960s, was to build upward, fast, and cheap. Tower blocks went up everywhere, and to speed things along, builders turned to a method imported from Denmark called the large panel system. Instead of constructing a building piece by piece on site, entire walls and floors were cast as giant concrete panels in a factory, trucked to the location and stacked together like enormous bricks by a crane. It was quick, it was cheap, and it needed far less skilled labor. Ronan Point in Canning Town in East London was one of these, a 22-story tower assembled from these precast slabs. Construction finished in March of 1968. Families moved in. 2 months later, on an ordinary spring morning, it fell. The flaw sat right in the heart of how the building was held together, and it comes down to a single idea: load paths. In a well-designed structure, if one part fails, the weight it was carrying has somewhere else to go. It flows around the damage through beams and connections into the rest of the frame. Engineers call this redundancy, an alternative path for the load. Ronan Point had almost none. In this large panel system, the walls were the structure. Each concrete panel simply rested on the one below it, holding up everything above through little more than the weight pressing down and friction at the joints. There was no separate steel skeleton threading it all together, no beams to carry the load sideways if a wall vanished. The panels were tied to each other only weakly, and when investigators later examined the joints, they found some connections poorly made, and in places, gaps that should have been packed with solid mortar stuffed with newspaper and rubbish instead. On top of all that, the Danish system had been designed for buildings of about 6 stories. At Ronan Point, it was stacked to 22. The whole tower was a pile of heavy panels balanced on each other, quietly depending on the assumption that no single wall would ever be pushed out of place. And that assumption met the one thing nobody had properly accounted for: ordinary domestic gas. Ivy Hodge's flat, like the others, had a gas cooker, and overnight, gas had been leaking from a connection to it, unseen and unsmelled enough to matter, gathering quietly in her kitchen in the small hours of the morning. There was nothing dramatic about the leak. It was the sort of fault that in almost any other building would have meant at worst a nasty bang, some broken windows, a fire brigade call-out. The pressure that explosion produced was modest, later estimated at well under 10 pounds per square inch, low enough that a person could survive standing right next to it, which is exactly what Ivy Hodge did. But that same modest pressure was more than enough to do the one thing this particular building could not survive. It pushed a load-bearing flank wall panel outward, out of the corner of the flat and out of the tower entirely. And the moment that panel left, the assumption the whole corner rested on was gone. With the flank wall blown out, the flats above Ivy Hodge's kitchen suddenly had nothing beneath one corner. The panels that made up the 4 flats above her had been resting on that wall, and now they had nothing to rest on, so they fell. That corner of the 18th, 19th, 20th, and up dropped down onto the flat below, and here is where a small explosion became a catastrophe. The falling weight of those upper floors slammed onto the 19th floor level below the blast, which had been built to bear a steady load, not a sudden hammer blow from above, and it gave way too. And then that floor's debris fell onto the one beneath it, and that one failed, and on it went, the corner of the building unzipping downward floor by floor, each collapse feeding the next, all the way to the ground. Engineers have a precise name for this: progressive collapse, when the failure of one small part triggers a chain reaction far out of proportion to the original cause. The entire southeast corner of a 22-story tower came down in seconds. It was the early morning hour, when most residents were still in bed away from those corner rooms, that kept the toll to 4 dead and 17 injured instead of many times that. The response was immediate, and it reached far beyond one building. A public inquiry, the Griffiths Tribunal, was convened within days, and its conclusion was as unsettling as the collapse itself. The failure was not caused by shoddy building work alone, or by some freak event. It was inherent in the design. A building assembled this way, it found, could suffer this kind of disproportionate cascading collapse from an ordinary accident, and that was a property of the system, not an accident of workmanship. The word that entered the language of engineering from this tribunal was disproportionate. The idea that a minor local trigger should never be able to bring down a structure far out of proportion to itself. British building regulations were rewritten to demand exactly that. Buildings above a certain height now had to be designed so that if any single load-bearing element were removed, the structure would either bridge over the gap or fail only locally, never unzip. Structural ties, the steel connections knitting panels together so loads can find another path, became mandatory. Across the country, existing large panel blocks were surveyed, strengthened, or in time pulled down, and the method itself fell out of favor. Ronan Point was repaired and lived in for years, but suspicion never left it, and in 1986 it was carefully taken apart, floor by floor, partly so engineers could study its joints, and what they found in those connections only confirmed how precarious the whole system had always been. What makes Ronan Point haunting isn't the size of the explosion, it's how small it was. A single leaking gas connection, a struck match, a bang a person could survive, and a modern tower shed an entire corner because there was no second path for the load to take. The disaster wasn't in the spark, it was in a design that had quietly bet that nothing would ever go wrong in exactly one spot. So here's the question worth sitting with. In the systems you rely on every day, your home, your workplace, the things you assume are solid, how many of them are held up by a single point that has simply never been tested yet? Tell me in the comments. Next time, we're going underwater, to a walkway packed with people at a hotel dance that failed because of one quiet change to a connection detail nobody thought was important. If you like disasters explained properly, with the engineering laid bare, subscribe and hit the bell so you don't miss it. See you in the next one.